Hi students, okay, in this next Gauss law video, we'll be exploring a few more consequences of Gauss law. The first one that I'd like you to become familiar with is the electric field due to a plane. So we begin talking about a plane because there's nothing stopping us from getting charged on a plate rather than on a sphere, and so that is a perfect physical example of an electric field that exists above a charged plane. Now, the simple mathematics that's available due to Gauss law demands that there not be warped fields like there would be in the case of a very small plate. So, essentially, we derive the electric field of a plate by assuming an infinitely large plate. So we'll presume that this plate is extremely large to begin with, and then we'll ask ourselves, how well does that compare to physical situations? Now, Gauss law, we're always making these Gaussian surfaces in order to implement Gauss law. So, in this case, essentially, what it comes down to is a calculation of the field at any point above the plate based off of this geometry. The result that we get from this analysis tells us that the field at any point above the plate is given as the charge on the plate divided by the area of the plate, and also divided by 2 times our constant epsilon naught from the previous video. Now, you may say, how can you determine the area of an infinite plate and the charge on an infinite plate? It's really not so much about tallying the entire thing up as much as finding an area and determining the charge within that area. In other words, we call this a charge density. So you will also see this written like so, where sigma represents the charge per unit area. Now you will also see an electric field that looks very similar to this next week when we have 2 plates, but it isn't quite the same because there are 2 plates. So it's important to remember that this is the equation for a single plate. We may also want to look at the geometry of the electric field. So it looks something like this. Now it may be a little bit surprising that the electric field is so straight up and down, but if you think about it, all the other directions must cancel due to the symmetry of this plate. Now, this presumes positive charge on the plate. If negative charge instead resides on the plate, then the arrows would point toward the plate rather than away from the plate. It's also important to remember that a small plate will not exhibit exactly this, at least not far away from it. Along the width of the plate, you can see that the field lines in the middle are relatively straight up and down, at least close to the plate. As we approach the edge of the plate, the field begins to become warped because there is nothing on the outside of the edge to counter the sideways components of the field. So, we can expect that this equation will hold in the case that either the plate is extremely large or in the case that we're very close to the plate. You can see how this might be the case because if we made this plate very much larger, then the influence of the sides of the plate would become quite small. Also, if we zoom in so that we're no longer far from the plate out here, but instead are very close to the plate, then we can see that it looks like a very large plate from that close distance, and it mathematically behaves like a very large plate from that close distance. Let's take a quick calculation just to get a sense of this. Now we can expect that we can fit approximately 5 nanocoulombs for every square centimeter on our plate. If that's true, then at first we need to convert to SI units to ensure that the electric field is also expressed in SI units. We can see that the charge density in this case is going to be 5 times 10 to the negative 9 coulombs, because of nanocoulombs, divided by 1 square centimeter, which is the same as 0.01 meters squared, or 0.0001 square meters. If we take this through our calculator, we'll find it to be 5 times 10 to the negative 5 coulombs per square meter, or you could also write this as 50 microcoulombs per square meter. Okay, once we have this, then let's go ahead and just run the rest of the calculation to determine what the electric field is. The electric field above the plate or below the plate is going to be equal to 2.8 times 10 to the 6 newtons per coulomb. So, this gives you a pretty strong E field just trying to cram together 5 nanocoulombs on every square centimeter. Like I said before, it's very difficult to pile on a lot of charge. Let's revisit our metallic sphere. Again, it's a hollow metal sphere, and so when we have it cut open in only two-dimensional space because we're dealing with a two-dimensional drawing, but you can imagine it as a hollow ball. Inside the ball, we'll place a charge. To make it interesting, I've made it a negative charge. Numerically, that is negative 2.3 nanocoulombs. Okay, so we have this charged ball in the middle, and we want to know what the response is in the middle. Imagine, if you will, what the E field is surrounding the charge. Please keep in mind that we said that there cannot be E fields inside of metal if there are no charges inside the metal, but there are charges inside the metal in this case, and so it's perfectly fine for E fields to be inside the cavity. However, our treatment of metals before showed us that the E fields cannot reside inside the metal itself, only inside the cavity that is inside the metal. If we draw our E fields, it should look something like this. Now, to figure out what's going on, we need to try to use Gauss' law again. Let's create a Gaussian surface at some point inside the cavity, at some point inside the metal, and at some point outside the metal. I've created 3 Gaussian surfaces so that we can analyze the electric field at 3 different locations. The yellow location, the pink location, and the aquamarine location. So, let's take a look at this one by one. We know that the electric field inside the pink location must be 0 because it's located within the metal itself. Now that's an interesting statement. If the electric field is 0, that means the entire flux is 0. If the entire flux is 0, then that means that according to Gauss' law, the total charge enclosed divided by some constant means that the total charge enclosed must also be 0. How is it possible that the total charge enclosed by the pink circle is 0? There's only one way for that to be true. If there is negative 2.3 nanocoulombs of charge inside the cavity, there must also be positive 2.3 nanocoulombs of charge somewhere inside the cavity. Can you think of where it would be? If you guessed on the inner surface of the metal, then you guessed well. However, you don't get something for nothing. So if we have this positive charge on the inside of the surface, then we must have extracted negative charge from it in order for that to happen. The negative charges will reside on the outer surface. Here, this set of charges acts to exactly cancel the inward-facing field that this charge demands. Now that we're outside of metal, I'd like for you to take a look at what this might look like from the outside. On the outside, our sphere looks like this. We cannot tell that there's a cavity inside. We cannot tell that there is a charge inside. We can't tell anything. And as a matter of fact, that's an interesting feature of nature when it comes to Gauss' law. What happens inside a conducting sphere stays inside a conducting sphere. We only know that this sphere is charged on the outside negatively, with negative 2.3 nanocoulombs of charge. The blue Gaussian surface, or aquamarine Gaussian surface, is easily calculated, with the typical electric field due to a point charge, where r, in this case, is the distance from the center of the sphere to the location of our Gaussian surface, and our k is our normal Coulomb constant, and q, in this case, represents the enclosed charge within the sphere, or the charge residing on the surface. Notice that we will still end up with inward-facing electric field lines. Now this is interesting because we didn't necessarily know that that was the case before, but if we investigate the inside again, then we wouldn't be particularly surprised to notice that the electric field coming in is cancelled in the metal, but continues after the metal. This is due to the fact that the positive charges are on the inside available to continue the electric field. The negative charges are on the outside, available to pull electric field, but inside, a counterfield has been set up by the charge separation to make sure that there is zero field inside the metal itself. Now this all might make sense to you, but I'm really going to challenge it this time. What I'm going to do is move the charge over. And now a really interesting effect is about to occur. You see, if we carry the pink Gaussian surface anywhere inside the metal, all the way up to the very edge of the metal, we should get zero electric field. This will remain true. As soon as we come to the inside of the surface, we should then have, suddenly, an electric field. But how is that possible for the charges to be distributed in this way? As a matter of fact, they're not. The charges have a distribution that is a little bit more like this now. Despite this, the charges on the outside of the metal have no information about what is happening on the inside. Information cannot be transferred from the inside to the outside because the metal is preventing E-fields from being transferred. Again, we are in the position where we do not know what's happening inside the metal, and therefore the charge distribution on the outside of our shell is actually still the same. In other words, if you have a charge on the outside of your hollow metal sphere, you cannot know whether there's a charge inside the sphere, whether there's no charge inside the sphere, whether there's a charge in the middle, or whether there's a charge off-center. None of those things are available to you as an observer outside the sphere. Gauss' law has a lot of applications. In your homework, you'll be primarily paying attention to the symmetry aspect of Gauss' law. Keep in mind that if you have a symmetrical situation, such as the outside of our sphere, then you can anticipate that if we were to only consider half of the sphere, we would have half of the flux. If we were only to consider 1/4 of the sphere, we would only get 1/4 of the flux. And so that symmetry actually makes calculations much, much faster. This is the end of Unit 1. Please, please, please feel free to contact me with questions. And don't forget to do your practice homework.